400 foot long.
All right, let's get started. Okay, we are back off the heels of what I would say is was an incredibly successful ASCE Virginia's conference. That was our first time hosting. I may be a tad biased, but I think we knocked it out of the park, and so I think our students did a fantastic job. We are in, they're not calling it Dead Week anymore, they're calling it Pre-Finals Week. So.
Stress relief week.
Okay.
It's not really.
But,
that's just kids.
So in the land of steel design, what I call this week is tying up loose ends, because there's two topics that we have left to talk about that we haven't discussed in significant detail that I think we kind of need to do our diligence for. One of them I think you could probably predict, which is shear. We've been, throughout this whole time discussing beams, we just sort of said, shear's not a big deal. And to be frank, it hasn't been. But it can be a big deal in certain building applications and most bridge applications. If you're dealing with transfer elements in building design that are subjected to unusually high shear demands, you kind of need to roll up your sleeves and do that properly. And if you're ever designing plate girders in bridges, plate girders, because you are tailoring the sizes of the flanges and the webs in order to resist the load demand, shear becomes a little bit of a different situation altogether. And so understanding shear, I think, is important. On Wednesday, what we're going to do is we're going to discuss a phenomenon that affects both columns and beams, which is called local buckling. And local buckling is when, instead of the whole column buckling, maybe just the flange buckles or just the web buckles. And again, that can happen with built-up sections, with plate girders and things like that. It can definitely control your design in bridge land. And so that's sort of what we're talking about today is, on Wednesday, is tying up loose ends. So with that, let me go ahead and pull up the lecture today. What I'm going to do for the first part of this is I'm going to just touch on a brief coverage of transverse shear. So this is kind of a greatest hits from what we covered in Engineering 216, Mechanics of Deformable Bodies. And then I'm going to discuss how that impacts design of steel W sections when subjected to shear. And then we're going to do a quick example on how to compute shear capacity, and we're going to see if we get the same answer that we're getting in Table 3 too. Now, I'm going to do something a little different for this assignment and for what's coming for this homework. And it's going to involve you needing to dig into the specification, probably a little more than you have needed to throughout the semester, but I have a reason for that, and I'll get into that here in a bit. So let's get into a brief coverage of shear. We're going to talk about transverse shear stresses today. That's sort of our topic of discussion. Okay. Now, what we're doing for today is I want to make sure that you all understand the effects that shears generate on flexural elements. You know, I have here on the right, I have a simply supported beam, and I put a concentrated load in the middle. So I think by now that you recognize that the shear diagram has this sort of stair-step approach to it, or the stair-step feature to it, and then the moment diagram is linear and peaks at the top. And hopefully, after having me for CE 312, you all are able to construct that. I don't think there's anything that's all that confusing about that, right? Okay. So from a mechanics perspective, one of the questions that we want to ask is about the shears. We know that bending stresses or bending moments generate stress. I mean, we can compute sigma equals my over I. We can compute the moment of inertia, take a bending moment from the moment diagram, and we can compute those bending stresses pretty easily. But the question becomes, do the shears generate stress themselves? The answer is yes. Okay. An easy way of discerning that is to look at what I got here on the screen. Okay. So I have here, what I've got is the beam, again, under the concentrated load, but what I've done is I've sliced out a little bit of, a little width, a little differential element, and we'll say it's dx wide. I drew it a little bit of width to it so we can kind of see what's going on. But say about this element? So, first off, I would propose that this element is subjected to a constant shear, right? Because on the left and on the right side, the shear is the same, right? It's one of the reasons why I'm using a simply supported beam with a point load in the middle, is because the shears are constant. But the moments are not. The moments are linear, okay? So what's happening with the moments is that I have a change in moment from one side of the element to the other. Like I have a little bit of a low moment here and a high moment here. Y'all see that, how the moment changes? So if the moment changes, what that causes a problem with is equilibrium, okay? Because if I have a different moment on either side of the element and I sum forces in the x direction, I would get that they would not equal zero if it weren't for an additional stress that it maintains equilibrium. And that additional stress is what we get from transverse shear. So that transverse shear has to be present in order to maintain equilibrium. And an easy way of trying to, okay, so that's sort of the math theory way of explaining it. Let me give you sort of a common sense way of explaining it. So I have here this is just my little calc book that I keep all the example problems in. And let's say I were to take this problem and take this book and bend it. Now it's pretty easy to bend. I mean, here I am, I'm taking it and I've got a heck of a deformation on that. And I was able to do that pretty easily with just my bare hands. Now, how many of you have ever done any type of woodworking? I'm just curious. Anybody ever done it? Okay, all right. So imagine that I were to take, now that's scenario one, me just taking this and just bending it with my hands. Now let's say I were to take this book and take it down to the woodworking shop and get some, wood glue and glue every single one of these pages together and then put it in a clamp it, let it sit overnight. Now try and bend it. Is that going to be all that easy? No. But here's the thing. Now let's think about this from an engineering mechanics perspective. Did I change the moment of inertia of the beam at all? No, it's still really the same beam. And I would argue I really didn't grossly change the mechanical properties. I mean, this is pretty much wood. I mean, it's just really, really thin strips of it, that's been processed. But something about adhering these transverse plies together suddenly changes the stiffness of the element, okay? So here's what's going on, okay? The missing force from transverse shear is at work. So like I said, the bending moment changes from one end of the element to the other, so the bending stress profile changes from one element to another. So I might have some bending stress profile that peaks at sigma on the left side, but on the right side, it's sigma plus some increment. There's more bending stress on one side of the element than there is on the other, okay? And so if that's all that was going on, then the section wouldn't be in equilibrium. There'd be something else, there'd be something missing, okay? And I propose that what's got to happen is we have to develop these transverse shears between the plies. It's like what's going on here, right? The reason that it's so easy to bend this is because the pages freely slide across from one another, right? Once the pages are adhered together and they can't slide across one another, that's when I start to get my increased stiffness. So as I bend this, there is a transverse shear that is developed between those plies, okay? That's what transverse shear is all about. And you need that force in order to maintain equilibrium of the beam, okay? Now, if we were in Engineering 216, I would derive this formula and we would go through all that. This is not Engineering 216. You should have seen this before. So I'm not deriving it for you. I'm just summarizing it for you, okay? Now, there are 4 really fundamental formulas for stress in the land of mechanics and materials. So we've got axial stress, we've got bending stress, we've got stress from torsion, and we have this. And that's our, I know if you take me for mechanics and materials, like the first, I'd say 60% of the class is just focused on really these 4 fundamental mechanical responses. Axial load, bending, torsion, and transverse shear. Transverse shear is sort of what we do last, and then we get into more circle and things like that. Now, in order to compute the stresses that you get from transverse shear, you need 4 terms, okay? So the first term that you need is the shear force that's applied along the section in question, and that's a constant, right, in terms of computing the stresses. Even when you're computing sigma equals my over I, the bending moment is a constant at the section of interest. Doesn't mean the bending moment is constant across the beam, it's just constant where you're cutting your section. So the shear force is constant, the moment of inertia is constant. The 2 things that can vary are Q and B. Now Q is what's called the first moment of area, so it is the area above the section cut in question times the moment arm. And that, I mean, again, we're not getting into transverse shear stress computation, so I'm not all that worried about going about that. What I'm actually more worried about discussing right now is the variable B. Now B is the width of the beam, okay? Now one of the things I want you to pay attention to is that the beam width can be variable, and I also want you to pay attention to the fact that B is on the bottom of the expression. It's on the bottom of the fraction. So what were to happen, let's just think about this mathematically. So tau is the shear stress. What would happen to the shear stresses if B was really big and suddenly got very small? What would happen to the tau value if B suddenly decreased in value? What would happen to tau? It would go up, right? The shear stresses would suddenly increase if B were to suddenly change in width. Does that happen in the real world? Yes, it does. It happens in I-shaped cross sections. So if you look here, so here I've got bending stress profiles and shear stress profiles, and I'll show you what it looks like. So if you ever look at a rectangular cross section, the shear stress profiles are sort of parabolic. You have 0 shear stress at the top and bottom. The biggest shear stress is in the middle, and you can compute that using VQ over IB. And you can compute that down here below, but what happens is, here's something happens that's really interesting. So what happens is, so you start, on the extreme fiber and work your way up, or work your way down. So I'm just starting here at the bottom. So this is your B value. So the distance between my fingers is the B value. Right here, right here, right here, bam. We have a sudden drop in the width of the beam. So what happens to the shear stress is we go bam, 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 whoa, sudden increase in shear stress. And so if we look at this from a mechanics perspective, we find that if we were talking about I-shaped cross sections, the section of the beam that is primarily responsible for resisting the shear stresses is the web, okay? It is the web that is there to ensure that the beam has adequate shear capacity. So when we look at the specifications regarding shear capacity of W sections, it's going to primarily focus on the web. Does that make sense? That's why when I'm talking about shear capacity of W sections, I'm really going to be talking about the web. That's what our main focus is. So let's talk about shear capacity. Let's talk about what happens. Let's talk about specifications, and let's get into this. Now, before we get into this, I want to preface something in advance now. One of the things that I think I've done, and there's been reasons for this, because I think the first time that you look at the specifications, it can be kind of daunting. But what I've tried to do for this semester, since this is your first time being exposed to a structural specification document, is I've tried to do what I could to sort of distill the information that's in the specification to only that which you need to know. But at the same token, or at the same time, I need to educate you all as engineers. So what you're going to find in this lecture is somewhat of a lack of coverage of, full-blown equations directly in the slides. For this homework, you're actually going to need to open up the specifications and actually read them and see if you can follow them. And I think you need at least a couple of assignments where you need to open up the specifications and read it and make sure you understand it. Because it is highly possible that you're going to get out of here and be faced with a design situation that I didn't teach you how to do, okay? And you all need to be able to open up the spec and read it and understand it. And so if we're going to do that, I wanted to kind of do it on something that's a little low stakes. As we've seen, shear capacity of W section hasn't mattered all that much. but I do want you to be able to understand how that works. So I just wanted to mention that. Okay, now when we're assessing shear capacity for steel I-beams, like I said, we mostly focus on the web, not the flanges. We have two things that we've got to concern ourselves with. The first is shear yielding. So that's what we're saying about shear yielding, is that that's full plastic capacity of the web and shear. So really all we're doing is taking the area of the web, which is DTW, and multiplying it by a limiting stress. And what is that limiting stress? The yield stress times 0.6. There's that 0.6 popped up again. Remember, the difference between shear yielding and normal yielding is 0.6, and that's not a factor of safety. That comes from the yield criteria that we use for ductile materials. The other thing that can happen is shear buckling. Let me see if I can pull up this shear buckling video, because I think it shows it a lot better than I could ever fully describe it. So now we're back recording. So how do we get around fixing this? Well, if you have a shear problem in the real world, the way that you fix that is one of two ways. You either make the web thicker or you include shear stiffeners, okay? So one of the things that you ought to check out is if you're ever driving around and you see an old steel plate girder bridge, and when I say old, I mean something maybe from the 50s, 60s, 70s, something like that, take a look at the steel beam. You will see stiffeners all over the place. You'll see oodles and oodles of them, because back in the day, we were living in an environment where the labor was somewhat cheap in comparison to the materials. The materials were very expensive. So we were trying to shave every single pound of steel that we could off the bridge. And the way that we handled that is to just throw stiffeners everywhere. Whereas nowadays, it's sort of the opposite. We'll make a girder 5% heavier if we can avoid a lot of welding. So a lot of modern plate girders, when you're driving down the road, they'll kind of look like this. You might have a stiffener here at the support, but that's about it. So now that doesn't mean we don't use shear stiffeners at all. I mean, we do use them, but we only really use them when we can't get around it from an economy standpoint. In other words, if we have elements that are pretty slender and subjected to pretty high shears, then we kind of need to go about placing some stiffeners in there. And the process by which that you place those stiffeners is somewhat similar to how you lay out stirrups in a reinforced concrete beam. The math is different, the mechanics are obviously different. The process has some similarities. So for those of you that take reinforced concrete design, you'll find that for a simply supported concrete beam, you'll space your stirrups pretty closely together at the supports. Out in the middle, they kind of get spaced somewhat far apart. And the reason is because the shear diagram is pretty low out here in the middle. Near the supports, they're spaced pretty close together, because you got a lot of shear out there. So, okay, let's get into the specification. So first off, one of the things that you will find with shear that's a little different is shear is one of the few places where the phi value changes. Now, if you've had concrete design, you know that that's not unheard of in some areas. So for instance, for bending in concrete design, you have to actually compute what your phi value is. You have to actually figure it out based on the strain in the steel. We haven't really had that problem here in this class and in steel design in general. Usually it's just, it's a tension member. It's 0.9 for yielding, 0.75 for fracture. Move on. Whereas with this limit state, you have to actually figure it out. So what you do is you basically assess what is the slenderness of the web, okay? And so you're going to start to see a couple of measurements pop up here. So, and you'll get a little bit more familiarity with this on Wednesday. But what we do is we take a look at an I-shaped cross-section, and what we're interested in is sort of two parameters. So we have this term H. H is different than the depth because H is sort of accounting for those little rounded, sort of bevels that you get right there. And so what we're interested in is web slenderness, and then we're interested in what's called flange slenderness. The reason for the two is because we're only interested in half of the flange. We're starting to get into this discussion of local buckling, which we'll talk about in more detail on Wednesday. But basically, we're not concerning ourselves with whether or not the whole beam fails or the whole column fails, but if just an individual element fails. Okay, so the first thing we have to do is we have to determine what our feed value is. For most cases with a 50 KSI section, phi is 1. There are only a few cases where phi equals 0.9, and phi equals 0.9 whenever our slenderness violates this limit right here. So one thing I want everybody to do is I want you to turn to page 6, to chapter G. So that is 16.1 dash 70. 16.1 dash 70. We're way back in the specification. This is where chapter G starts. So what we're going to do first is we determine what our phi value is. And so our phi value is determined based on this limit here. For most W sections, it's 1. For a few cases, it's not. And so we're going to go through an example problem here where we assess this. But then I'm going to give you another homework problem where you're going to have to assess it again. And again, unlike some of my previous lecture notes, I'm not just saying, oh, here's the equations. I'm actually just saying, here's the specification. I kind of want you to review the specification on your own and see. Now, once you get the phi value, the next thing you need to do is you need to compute your nominal capacity. And the way that you compute your nominal capacity is you take 0.6 times Fy, okay? And then you take Fy times the area of the web, which in this case is dTW, and then you multiply it by this, CV1, okay? CV1 is a buckling reduction coefficient. So the idea is that if your section is going to be susceptible to buckling, then you would reduce the plastic capacity of your web based on how slender it is, okay? And the specification gives you a pretty easy flow chart to follow. So if your web slenderness is less than or equal to this value, then CV is 1. If your web slenderness is greater than this value, then this is how you compute it. In order to do this, you're going to need a web shear buckling coefficient, KB, and it tells you how to do that right here. And this is one of those areas where I kind of want you to read the spec and figure some of this out for yourself. I'll go ahead and tell you that I'm not going to put shear capacity calculations on the exam. So it's really just for this homework assignment. So the stakes are pretty low, but I want you to figure this out on yourself. The one thing I will add to this is that I think that the specification does a pretty good job of guiding you through this. Read these user's notes. Read the specification. This isn't all that difficult, okay? And in order to walk you through this, I kind of want to do a brief example to just sort of show you how this works. So we're going to compute PVN for a W24 by 62. And we're going to compute this for 50 KSI steel. Let me make this a little bigger here. So we have here a 24 by 62. Just so you're aware, we can look it up. And the capacity, if you look it up, is 306 kips. So, man, this cable is all sorts of things. There we go. So, before we do any math, I just want it known that we could just look this up. Okay? Okay. In this example, I actually don't even have written out. I don't have this one calculated, so we're going to do this one together. Okay. All right. So in order to compute it, let's see what we need. Okay. So in order to compute the capacity, first off, let's look up some properties for a W24 by 62. Okay, so in order to compute the capacity, I'm going to need the D value and the web thickness. So somebody help me out. For a W24 by 62, what is the depth? What is the web thickness?
Depth is 23.7 inches.
Okay, and the web thickness?
0.430 inches.
All right. Now, the other thing that I want to make sure that everybody's able to find, and this is probably the one thing in the W section table that we haven't looked at, okay? So if you look at the left side, the left page contains all of the dimensions, and the right page sort of contains all the properties. Now, if you look at the right page, the very first two columns should have a thing up top that says compact section criteria. We're going to know a little bit more about what that means on Wednesday, but for today, just suffice it to say that those are slenderness measurements of the flange and the web. So for the web, you should see a property that's H over TW. And what is that for a W24 by 62?
50.1.
Okay, is everybody able to find that? Okay, so that is, so if I took the height of the web and divided it by its thickness, I would get a slenderness of about 50.1. So you can sort of think of that as like a KL over R for the column. That's, or for the web, for the column. KL over R for the web, that's what that is. Okay. All right. Now I want everybody to go back to chapter G. So chapter G, 16.1-70. So okay. All right. Okay. So what we're looking at here is we've got a series of sections. We're going to go to section G2, I-shaped members and channels. Shear strength of webs without tension field action. I'll talk about what tension field action is here in a little bit, but because we're getting into some advanced stuff when we talk about TFA, but we'll talk about that here in a second. All right, the nominal shear strength of the web is this equation right here, okay? And then if you go on to the next page, it says for webs of rolled I-shaped members that meet this parameter, H over TW less than or equal to this, phi is 1 and CV is 1. So let's see if that's the case. So we know that H over TW is 50.1. What is 2.24 square root of E over Fy? Well, it's 2.24 square root of 29,000 over 50. What is that?
I got 53.95.
53.95. Do I have a second on that? So H over TW is less than, getting ahead of myself. E over Fy. So what does that mean? What is the spec telling us? Tell me what that means.
V is 1.
Phi is 1. What else is 1? CV. So, or CV1, I guess I should say. They actually changed that notation in this last edition of the spec. I'm not the biggest fan of it, but I kind of understand why. Okay. So, we've got this. So how do we compute the capacity? Well, what does it say here on 16.1-70? It says the nominal capacity, Vn, is 0.6 Fy AW CV1, which is 0.6 Fy, and then AW is DTW. Y'all see that at the bottom? So DTW C1 or CV1, which is 0.6 times 50 KSI times 23.7 inches times 0.43 inches times 1. And what is that?
I got 305.73.
305.73. So 305.73 kips. Do I have a second on that?
Yep.
And so PVN is just 1 times that. So VVN is 305.7 kips. And what did the table yield? 306. So now you can see where that's coming from. It's just everything in those tables is rounded to 3 significant digits. So that's where that came from. Pretty simple, right? I mean, it's really all not that complicated. But again, the 2 reasons that I held this topic off for so long is that it's not that consequential, but I want one topic where you have to actually read this and figure it out. And the best way of doing that is to give you a homework where it's a little bit more involved than this. I gave you a homework on a 30 by 90, and to be clear, you can probably look this up. I mean, you can look it up and get the answer, but I want you to be able to negotiate the specification, and so that's kind of the purpose of this homework. Now, one thing I will explain in the manual is that, so if you look at the section that we're looking at, it says shear strength of webs without tension field action. And then the section on the next page says if you're considering tension field action. So that's sort of why there's a CV1 and a CV2. Tension field action is very, very interesting in the land of shear design. It's kind of a nuts thing when you first hear about it, but it's really cool. Like you can actually do it in the lab and see that this happens. So the idea is that here's the I-beam, right? So let me put those flanges here. Let's put a stiffener here. And let's say that's my support. So what happens is, if you load this thing in shear, as we saw in that video, it buckles, right? But what happens when it buckles is that, you know, the web sort of folds in this way. So it folds in this way, and we sort of develop this like rippled region that kind of goes like that. Y'all remember seeing that in that video where it kind of ripples like that? The thing that's kind of crazy is that normally when we think of buckling as like, that's it. You load it, it buckles, it's done. That's not the case with shear. The reason is that in shear, the entire component that is undergoing buckling is fully restrained on all 4 sides. So the crazy thing about shear buckling is that you can keep loading it. You can actually keep loading it after it buckles. And what happens is, this steel over here is useless. It's all buckled. But in here, you can actually keep resisting load, and it develops this sort of field that resists the load in tension, because this is the segment that's being yanked on. And steel loves to be in tension. So you can actually develop what's called tension field action. That's what that TFA stands for. But you're starting to get into that's some pretty advanced stuff with steel design. Like if I teach a graduate course on steel design, I cover how to do this. None of the stuff that you see in the manual is hard. It's more just about having the forethought to know that it's a possibility and then just seeing how the math works out. It's really not that complicated, but it's pretty crazy. The beam sort of turns into a truss because you've got these elements resisting load that way, and it sort of starts to behave like a truss. So, but yeah, so this is pretty cool stuff. All right. Any questions about any of this? All right. So I'm going to pull a couple things up to close this out. First off, I kind of want to show you this upcoming homework. So this is homework 6-8. So basically, I'm just having you compute the shear capacity of a section of A90 of W30 by 90 of A992 steel. One thing I don't believe I said in the problem, but if you need, assume it's unstiffened. Assume there are no stiffeners. I don't think that really matters all that much, but if you need to make an assumption, assume it's unstiffened. And this is one that you could look up in table 3.2, but I actually want you to negotiate the specification. I want you to read this and investigate it and see if you understand it. Okay. And the last thing, I just want to give you a taste of what we're going to talk about on Wednesday is this idea of local buckling. Just to set the stage, and again, this whole week is about tying up loose ends. This is our expression for column buckling. This is the curve that we use to predict the capacity of columns. This is the curve that we use to predict the capacity of beams. Both of these curves assumes that local buckling doesn't happen. And what is local buckling? This is local buckling, okay? So I have some analytical pictures and some real pictures, but I'll show you the real one. The real one's kind of hard to see. But here we have an element, so this is a column, and these are a series of beams that's framed in. And what you can kind of see is that the flange sort of gave up, right? The flange gave up before the whole thing did, okay? Now what we're talking about is the difference between, like if I have a W section loaded in compression, this would be a view of the entire column buckling globally. The whole thing buckling left to right. Whereas local buckling is what happens when an individual flange or an individual web gives up. And for that to happen, the section's components, the flanges and the webs, have to violate a certain slenderness limit. Okay? That's what those compact section criteria values are all about. It's not the whole column buckling or the whole beam buckling, it's the individual components buckling. And I have some videos that show what this actually looks like in the lab. Like I have a local buckle and I have a, let me see if this video here loads up. I mean, videos are awesome. So.